All right, welcome everyone to our 11th live stream geometry session. So we have two other people here with us right now, and I'm sure more will join later. So this time I chose a bunch of problems from the China Northern Math Olympiad and the Saudi Arabia team selection test for the Balkan Math Olympiad. So let's jump into it. I'm going to share my screen. Hold on just a sec. All right, can you guys see it? All right. So this is the 2018 China Northern Math Olympiad. So we have a triangle ABC. Let me maximize it. And we label the orthocenter, incenter, and circumcenter. All right. That's the circumcenter. I got better with GeoGebra, so I know how to do all the shortcuts for this. And H is the orthocenter. There we go. That's H. And we let AO, AI, and AH meet the circumcircle at D, E, and F. So let's shrink this a little bit. Good. That's nice. It's just D, E, and F automatically. CD intersects AE at M. So I'm probably going to want to shrink the diagram a little more. And EE intersects AF at N. And so I'm going to relabel these M and N. And we want to show that MN is parallel to BC. Just a second. That's M. That's N. And now I'm going to try to delete some of the excess so that the diagram looks less complicated. Okay, let me draw this one too. Hide, 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 hide. I'm going to want to draw that. All right. So DF is parallel to BC. That's kind of a well-known fact because AH and AO are isogonal. So angle BAH is equal to CAO, and that's kind of a simple angle chase. And so because of that, the arc BF, BAH, and CAO intercept equal arcs. So arc BF is equal to arc CD. And so from there, BF has to be parallel to BC. But how do we show MN is parallel to BC? Let's see. It's an interesting question. I wonder if we want to like extend AH and CD. I'm not going to do that yet, but maybe that would help. So AD is the diameter. E is the midpoint of this arc. Let's see. How would we show that? I wonder if ND is tangent. No. So by power of a point, we have MD times MC is equal to ME times MA. We also have NF times NA is equal to NE times NC. Let me label this point right here. So we know, basically we know the reflection of H over G is F. Isn't this just Rhimes' theorem? How is it Rhimes' theorem? Maybe you might be right. So if MN were parallel, that would mean that ANMC is cyclic, basically. Yeah, I think that's what you're saying, right? So yeah, yeah, we have to show ANMC is cyclic, and is that obvious? Yeah, because arc EF is equal to arc EB. Okay, yeah, it's a simple problem. All right, so I'm going to start writing up the solution. Just a second. All right. Okay, so basically angle FAE is equal to angle ECB. And so that means the quadrilateral ANMC is cyclic. And so basically from there, by Rhimes' theorem, MN is parallel to DF. I'm going to write this out a little bit more. So first we have, I'll just write it out fully. So AH and AO are isogonal. That's kind of well known, but I'm just going to write it out fully. So angle BAH is 90 minus angle B, which is...
Hello, everyone.
Hey,
Hello,
Rodrigo.
Michael.
Thanks for joining. Good to see you. Let's see who's on right now. Okay, so you have joined, and I3435 is also on. All right. So this is the first problem, and we've just solved it, so we're writing it up. But yeah, you can see the problem up here. Here's the diagram. So this is the China Northern Math Olympiad. So I'm just doing a quick proof that AH and AO are isogonal. So that is a fairly well-known fact, but I'm just writing it out. And that is equal to angle OAC. Okay. I'll leave that. That's because OAC is isosceles. So basically, that means arc BF has to equal arc CB. So CAB, and then AE is an angle bisector, so E is the midpoint of arc BC. So just a heads up, there is a problem using Sharpie double later. So I think that might be like the 5th problem. I haven't solved it yet, but I saw from the initial configuration it looks like it. So that will be fun. So from these two, we can conclude E is the midpoint of arc FD. So yeah, maybe there was like a faster way of going about this, but I'm just gonna write it like this. So E is the midpoint of arc FD. And so that means that angle FAE is equal to angle ECB. So I'm going to write this out. So, whoops. I'll write it like this. So angle NAE is equal to angle FAE is equal to angle ECB is equal to angle NCM. Okay. And so ANMC is cyclic. And once we know that, it should be fairly easy from there, because then we have angle MNA. So actually it's 90, but we don't even really need that fact. So angle MNA is 180. So this is basically just proving lines here. Is 180 minus angle MCA is 180 minus angle DCA, which is equal to angle DFA. And so therefore MN is parallel to DF, which is parallel to BC. So I guess really, I'll just add this up here. So BC is parallel to FD from this step above. So if we combine it, then we get MN is parallel to FD, parallel to BC, and that solves the problem. All right, so I'm going to move on to the next one. This one wasn't too hard. All right. So we have a triangle ABC is inscribed in a circle O. I like doing it this way better. Now I can call the center O. Oh, whoops. No, let me delete this guy. So O is just center C. The bisector of ABC intersects the circle at point D. Let me move this up a little bit. My bisector. Oh, now I got to shrink it a little more again, because the tangents at B and C intersect at P. So maybe there will be some median stuff. We'll see shortly. Let's see. It's tricky. Okay. I'll just do this for now. So the tangents intersect at P. PD intersects AC at E. Obviously, PD is like the perpendicular bisector of BC. So it intersects AC at E and it intersects the circle at F. F is going to be the midpoint of arc BAC. I'll let M be the midpoint of BC. Did I do this right? Something here is off. So PD intersects AC at E and the circle at F. Yeah, something here is off. I thought I had this before because I looked at it briefly. Let's see if we can salvage the problem, or else I could just go look it up again. The bisector. C at E and intersects the circle at F. M. Yeah, I know I had this working before, so let me see. I think the bisector of, you're right. It's the bisector of ABC, not BAC. Okay, so I got to redraw this a little bit. Good point there. The bisector of ABC intersects the circle at D. We still have point P. PD intersects AC at E and the circle at F. I guess, yeah, the second intersection is at F. So if M is the midpoint of BC, we want to show M, F, C, and E are cyclic. And you might already see it's like an angle chase or something. I don't know. I'm not sure how hard of a problem it is. Let's see. So check it. Yep, MFC is indeed cyclic. It looks like it's just an angle chase, but I don't know, maybe it might use Pascal's theorem or something. So yeah, OM and P are collinear by symmetry. Let's see. Does drawing this the median help? It could. So yeah, I'll draw this median. Let's see. Is ME I think maybe it's equivalent to saying ME is parallel to BD, I think, right? And then that would be an angle chase. Yeah, so we want to show ME is parallel to BD. Probably looks like probably some spiral similarity or something. I'm just throwing out words here, but let's see. So I'm sure, like, if we could show E is the midpoint of GC, that would solve it, because that would mean ME is parallel. And maybe that's just projective geometry. So let's see, can we show E is the midpoint of GC? So if we project D through G, E, and C onto the circle, we get BFC, BFCD really. So, and BFC is harmonic. Yeah, so that proves it. All right, so I'm gonna start writing it up. So this proof used a little projective geometry. So for those of you that don't know it as well, I have a couple of videos on my channel, but you can ask me about it in the Discord more too. All right, so basically I'm going to prove that E is the midpoint of GC using projective geometry. So we have GC E, and I'm going to write it like this, in the point of infinity. So that cross ratio, if we can show that's equal to 1, then that means E is the midpoint of GC. So projecting onto circle O, that is equal to, well, first I'm going to remark that D is the midpoint of arc AC, so the tangent line at B to the circle, how do I say this, is parallel to AC. So let me write this out fully. All right, and so that means that the tangent to the circle at B is parallel to AC. And so now we can do our projection. So projecting through B onto the circle, we have G, C, B, the cross ratio BCF and B, and that's because the tangent at B is parallel to GC, from what I just said. So then we have BCFD, and that cross ratio is going to be equal to -1 since BFCD is harmonic. So, so I'll write this out. So, the tangents at B and C and DF are concurrent. So by the definition of a harmonic quadrilateral, that means that BFCD is a harmonic quadrilateral. And so that means that that cross ratio that I just mentioned is -1. So BCFD is -1. Okay. And so that means that GC, that means that this cross ratio is -1 by transitivity. So then it follows from there that E is the midpoint of GC. All right. Let me delete that $sign. And so then GE equals EC and BM equals MC. That would mean that EM is parallel to BG. Or I'll say BD. And then, so if EM is parallel to BD, now we can just use angle chasing. So we have angle EMC equals angle DBC is equal to angle DFC is equal to angle EFC. And so that means MFCE is cyclic. All right. So yeah, before I knew projective geometry, I'm sure this would have been a much trickier problem. But I used this fact. Ooh, I spelled harmonic wrong, so I get to catch it. Harmonic. But yeah, for those of you that haven't seen this, I'm saying BFCD is harmonic. That means the tangents at B and C are concurrent with the line FD. And harmonic quadrilaterals, they have a lot of useful properties. All right, so if unless you guys have any other questions, I will move on to the next problem. Let's see. Yeah, this Olympiad doesn't seem the hardest. I thought because it was China, maybe it would be like a harder one, but I think this China Northern is probably not as hard. So here we have a 2 circles problem. So yeah, I feel like I should probably do more of these 2 circle problems on my channel. So yeah, wait, hold on a second. No, I want to do it like this. All right. But yeah, so I think the next problems are going to get harder. So after these problems, I have the Saudi Arabia team selection test for the Balkan Math Olympiad, and those problems looked a little bit harder. The bisector of O1A02 intersects the circles at C and D. Okay. It intersects O1 at C and O2 at D. And then we draw this circle. So let me try to make this nicer. How do I do it? Let's see. Maybe something like that. Let me draw the circumcircle of BCD. And P is just any point on that circle. Let me hide some stuff. Rename. Actually, why did I draw this? Oh, because I need the bisector. Okay, so CP intersects O1. Okay, so we have points. This is E, and that's F. It's pretty nice. I didn't have to rename them. And we want to show PE is equal to PF. So that's kind of interesting. Wherever P is on this circle, PE is always equal to PF. All right. Let's kind of like power of a point a little bit, right? Because PD times PF is the power of P with respect to the circle. I wonder if PD is equal to CE. That looks like it. No, not necessarily. Let's see. Maybe congruent triangles somewhere. Are EA and F collinear? Looks possible. Yes. They are collinear. Let's see if there's a way to see that. So, yeah, then it would really just be an angle chase, right? So, if we can show angle CAF plus angle EAC is 180, then that proves they're collinear, and maybe that's just an angle chase. So angle CAF intercepts CAF is equal to DAF. Just trying to do the angle chase. So let's see. We want to show so 180 minus EAC is EBC. Are ED and D collinear? No. Feels like it should be an angle chase to prove that. Let's see. So we want to show half of angle EO1C. We want to show angle EO1C is equal to angle DO2F, basically. Just check that quickly, but yeah, EO1C, DO2F. Let's see. So yeah, let me draw. I don't know if drawing O1, O2 helps. Let's see. Yeah, if EA and F are collinear, then it seems like it. Let's suppose they were collinear. Would the problem be easy to finish off? Actually, that's equivalent to what we're trying to do. Yeah, okay. So basically, PE equals PF is equivalent to EA and F being collinear.
Let's see. Yeah, I thought it would be an easy angle chase, but yeah, maybe it's harder than that. Let's see. So angle DAF is equal to angle DBF. We want to show DBF is DBF equal to ABC? ABC looks like a smaller angle, although I'm not sure. Or we want to show DBF is equal to EBC. Let me check that. Yeah. Can we show DBF equals EBC? So maybe those triangles are similar. Yeah, we want to show, I think we want to show triangle EBC is similar to DBF. So that would be the same as saying DBC is similar to DEF by spiral similarities. Although that might just make it harder. Yeah, so what if I did like an angle chase? So, let's see, what would that mean if EA and F are collinear? Maybe I should go back to my power of a point idea. I don't know. So the power of P with respect to O1 is PC times PE. And the power of P with respect to O2 is PF times PD. Can I say anything about those powers? Let's see, so yeah, so PC times PE. I'm wondering if like I could use the power ratio lemma. So yeah, I'm pretty sure there's a simpler way than this. I'm just trying it for the heck of it. This circle. Okay, scratch that. But yeah, I know there's like a couple theorems where you like take the ratio of the powers of P with respect to the two circles. But yeah, I'm not sure. Yeah, I feel like there should be an easier way here. It feels like it should be angle chaseable. Yeah, like how do we show EA? Once we know EA and F are collinear, then we can finish with an angle chase. But how do we show that EA and F are collinear? Is it obvious? Is it just an angle chase to show that? So yeah, let me think of it. So if we can show angle EO1C is equal to angle EDO2F, like that feels like a pretty fundamental theorem, like EO1C equals DO2F. It feels like that has to have a decent proof. Angle EAB, I should have seen that. Yeah. All right. So yeah, you're using directed angles. I'm just going to kind of sweep that under the rug and just assume the diagram's right for a second. So yeah, angle EAB is equal to angle ECB, which is 180 minus, or which is angle PDB. Yeah, okay. So that solves it pretty much. So I'm going to start writing up the solution. And yeah, the next problems I think will be harder. Yeah, I feel like this one, yeah, I just couldn't see the right angles, but this one really isn't harder than the previous ones. Let me shrink the diagram just to make room. All right. Okay, so we can show EA and F are collinear by the angle chase. I feel like it might just cover up the diagram. Yeah, I hate that GeoGebra. They didn't change. It used to be draggable. You used to be able to drag the text box to the side, but they changed it so that you can't do that. So angle EAB is equal to angle ECB, which is equal to angle BDF. Just a sec, let me check that that's right. Which is 180 minus angle BAF. EAB, ECB. I could just add BDP, why not? All right, so EA and F are collinear. And once we know that, we'll draw that in. Now it's really just an angle chase because, yeah, I had this before, but how did I? Yeah, I'm just trying to remember here. So angle AEC is equal to angle ABC, and angle AFD is 180 minus ABD. How did I do this? Let's see. O1AC and O2AD are similar. I thought I had a proof in my mind that did it in O2AD. Oh, because it's angle bisector. Yeah, I forgot to use the fact that it's angle bisector. Okay, so good point. So AD, so this is because that's the angle bisector. And so, yeah, those two triangles are similar. And that pretty much solves it. Well, have fun at the zoo. Yeah, I love the zoo. But yeah, we do have a Sharky Devil problem later, so you may want to check that out on the YouTube. So see you. All right, so O1AC and O2AD are isosceles. And so we'll say and thus similar. Okay. And so from here, it's just an angle chase because angle AEC is half of angle AO1C, which is half of angle AO2D, which is equal to angle AFD. Okay. Sure. AO2D, which is equal to angle AFD. I'll just write it like this for completeness. And so that means, maybe I'll even add this. All right, so angle AEP is equal to angle AFP. And so that means that PE equals PF. All right. So I think this is the last one from the China Northern Math Olympiad. So I think we've already gotten through 3 problems. So the next ones will probably be harder. So this is the team selection test for the Balkan Math Olympiad for Saudi Arabia. So a lot of countries, they have their IMO team selection test, and then they have a separate team selection test for other Olympiads. So this is the case for Saudi Arabia. Whoops. So we have a triangle ABC. We want AB to be greater than BC. Actually, let me do it like this. Something like that. I don't like that. Let me do it. Something like this. Oh, actually, we want B to be at the top. Just looking at the way it's phrased. Okay, so like that. Okay. So let's draw the circumcircle. AM is equal to CN. All right. use the compass tool there. That's a fun tool in GeoGebra. AM equals CN. MN and AC intersect at K. Let's see. How do I? This is tricky. How do I want to? Yeah, something like that. Okay, so MN intersects. Let me shrink things a little bit. So here's point K. Whoops. P is the center of triangle AMK, or the center of the inscribed circle. Okay, so basically, and Q is the X center of triangle CNK, tangent to CM. All right, so let's see, this should be, this should work. So that's Q. I'm going to hide this, but I'm going to draw the X circle. So see, there we go. Let's hide some stuff. Yeah, let me draw. Okay, so oops. We'll draw that line too. Oh, actually, no, yeah, I'm going to want to label this and then hide it and then draw it. There we go. That looks pretty nice. P, okay, the midpoint of the arc ABC. All right, so let's draw that in. So this is the midpoint of that arc. I called it F. We want to show FP is equal to FQ. All right. Feels a little like congruent triangles, like maybe is FM equal to FN? Because maybe, yeah. So it looks like maybe triangle FMP is congruent to FNQ. Maybe. Let's see. So if we move things around a little bit, FMN is isosceles. I just happened to notice that. Oh yeah, and that's just Archimedes' theorem, actually, I think. So I think it's not hard to show that FMN is isosceles, because yeah, we can show that triangle FMA is congruent to FNC. Interesting. So is triangle FNQ congruent to FMP? That would also be very interesting. So I'm going to check it out. No, they're not congruent. They just have two of the same sides, which is interesting.
That is interesting. But yeah, it feels like there's got to be some congruent. Maybe triangle. So AM is equal to NC, FM is equal to FN, and we need to show FP is equal to FQ. So it almost feels like there has to be some congruent triangles somewhere. Just going to check if anyone joined us. Okay, so Raffaello and Rodrigo are on right now. Let's see. Yeah, maybe we could like apply Archimedes' theorem again. Not sure. Let me just try. I wonder what happens if we draw the perpendicular from F to PQ. I'm just going to try this for a sec. I mean, another thing, so the power of F with respect to this circle is FP squared minus the radius squared. And yeah, maybe we could do something with powers. I don't know. So there's the theorem, the difference between the powers of F with respect to these two circles is twice the distance between their centers times the distance from the point to the radical axis. So I wonder if that could do it. That might give us like a longer solution to this problem. Yeah, I feel like there's a shorter way. Yeah, it's so weird seeing that like FM is equal to FN, but they're not congruent. That just feels so weird to me. Let me draw that circle in one more time. Maybe it's like that. Maybe we could use the in-center x-center lemma somehow. So like maybe we have like triangle PQ and another point, and F is like, yeah, what if I drew the circumcircle of PFQ? I wonder if these circles always meet on that line. No. Huh.
let's see. All right, so yeah, I'm thinking through this. So FMN is similar to FAC, those triangles. Yeah, FA is equal to FC, FM is equal to FN. Yeah, if AM is equal to CN, maybe there's a way to use that to connect like the radii of these two circles or something. So the radius of this X circle is this, so KD is the semi-perimeter of triangle KNC, and so the radius of this circle is, or let me draw this point in G. Is F on the radical axis of those two? No, because so if I can show, let's say I drop a perpendicular from F to PQ. If I can show that 2FH times PQ is equal to this radius squared minus this radius squared, that would solve the problem. It's kind of a weird thing to show, but yeah, I don't know, maybe it could work. Still think, yeah, there has to be an easier way. So yeah, we have like 3 concentric circles basically. Huh. Rodrigo, do you have any thoughts so far?
Yeah, I think I was thinking about doing log cosines.
Yeah.
In triangles FBA, FBA, and FCQ. Because basically you know that FA equals FC. and you want to show that FP equals FQ. So, and the angles FCQ and FAP are very well known. So I was trying to deal with PA and QC. They are these segments, but yeah, I'm not going so far with that idea.
All right, yeah, it's interesting. Yeah, let me know if you find something. But yeah, we also have, I'm thinking about that way. I wonder if angles FPA and FQC add up to 180. No. So another way of saying it is we want to, if I could show the area of PFQ is, or twice the area is QD squared, is this radius squared minus this radius squared, that would solve it. But that's such a weird way to phrase the problem. Yeah, law of cosines, let me think about that. Actually, you know what? So if I draw the, something's weird here. Wait, I'm trying to see what's up with Archimedes. So Archimedes' theorem says if I drop a perpendicular from F to AB, let's see. Yeah, let me draw on the radical axis of those two circles. That would be, oh, no, the thing I said about area, I don't think is true. But I have another idea. Let's see. I don't know if this is good or bad, but I feel like I'm determined to find a congruent triangle somewhere.
Yeah, FMA is congruent to FNC. Let me draw that in. So FMA is congruent to FNC. Basically, I proved that in my video on Archimedes' theorem. And I want to show that FP equals FQ. That those angles almost look equal. I don't think they are. Let's see. Oh, wait a sec. Are those both 8.1? Yeah. So FA and FN are isogonal. Wait. That is very interesting. Those angles are equal. I feel like that has to be an insight. Angle PAF equals angle NFQ. Huh. For angle PFA equals angle NFQ. And then similarly, we'd have angle BFQ equals MFA. Wait, or no, angle BFN. Wait, what? One says 21.8, the other says 22. Wait, now I'm confused. Wait, so I said angle PFA equals angle NFQ. So then similarly, we'd have to have QFB equals MFA, but that doesn't. Wait. Yeah, these two. Yeah, I guess you can't make a symmetric argument. So, yeah. Yeah, that's quite surprising to me. I don't see immediately why that's true. So PFA equals NFQ. So yeah, what if we let the circumcircle, or what if we draw in a circle and we let it intersect AF at a point H? Then we want to show triangle PFH is congruent to triangle FNQ.
Hey, Michael, is it true that FB and M are cyclic?
FBMN? Let's see. I don't think so, but maybe. No, you might, hold on. Actually, no, it is true. Yeah, FBMN is cyclic, my bad. And that's just an angle chase. Yeah, let's see. Yeah, I'm thinking. Yeah, so a spiral similarity. Like, I wonder, a spiral similarity takes point B to another point. Let's see, what if I did this? Then FBH, we want to show this congruent to F. Wait a sec. Is FB equal to PA? No, QH would equal PA in that case. Are QH and V collinear? That almost looks true. Let's see. But it's not. Yeah, I'm just going to stop adding so much stuff and just start trying to think of a way. See. PFM. Okay. So yeah, maybe it would help to draw the center. Let's see. Where's the circle through AF and C? see. All right, we have Arabian Math on. Thanks for joining. So yeah, we have a tricky problem here. This is from the Saudi Arabia Balkan Math Olympiad team selection test. And we're trying to show that FP is equal to FQ. So yeah, you can read through the problem. All right, I'll spend another like 15 minutes on this and then I'll move on to another problem. But this still is already our fourth problem, so we're not doing bad on time. Yeah, whenever I see like a distance between a point and the center of a circle, I'm always thinking like use power of a point or something. Yeah, what can we say? So yeah, FMA is congruent to FMC. I'm having an idea here. Let me see how this is going to work. What if we reflect N over FC? So then Fn prime C is congruent to FMA, right? And basically, then we'd want to show Fn prime Q is congruent to FMP, I believe. Am I missing something? Oh, wait a sec. No. Is it? Let's see. Yeah, I feel like there's got to be some way. The fact that angle PFA is equal to angle NFQ, which we haven't proven it, but feels like there has to be a way to use that, and the fact that FMA is congruent to FNC. So that's kind of what I'm trying here. Yeah, it's kind of like trying to think how to do this. Like what if I reflect triangle? Like if I reflect triangle AMF across the angle bisector. So basically, let's do this. So basically Fm prime A prime is congruent to Fnc, and I want to show Fm prime P is congruent to Fnq. Let's see. So yeah, that would mean P A prime F is congruent to FCQ. Yeah, can we show those are congruent? So FA prime is equal to FA is equal to FC. So we know that these two triangles share a side. Can we then show that they're congruent somehow? We kind of know angle FCQ. Is angle PA prime M prime equal to angle BCQ? Yeah, this is a really random approach, but kind of interesting. Let's see. Actually, you know what? Let me try. No. Let's see. A prime F is equal to FC. see. I wonder if this is cyclic. Let me check. No. But AA prime, like it's kind of like, so FAA prime is similar to FM prime M. I mean, basically, yeah, we could draw this circle. Let's see. So F is the circumcenter of M prime MN, and it's also the circumcenter of A prime C. So yeah, that kind of lets us do some angle chasing. I'm going to just try this, and if this doesn't work, I'll move on to the next problem. So F is the circumcenter of those two triangles. And so, yeah, we can basically calculate see. I wonder if PAA prime is similar to A. Well, let me check that out. Wait, so it looks like PAA prime MM prime is cyclic. Is that just a coincidence? Because the, yeah. Okay. That is very interesting. I keep feeling like I'm just about to solve it. But so yeah, I want to show FPA prime is congruent to FCQ. And now that I know, so I'm guessing this is probably cyclic by an angle chase. We know A prime MM prime is cyclic because it's an isosceles trapezoid, but the fact that P lies on it, I would guess is probably just an angle chase. And so, let's see. So first of all, we want to show angle MA prime P is equal to angle FQC. So MA prime P is equal to angle MAP. So Wait, we just want to show angle MAP is FQC. That is just an angle chase. Okay, so I've shown, I'm trying to use angle side angle basically. And I've shown on these two triangles, FPA prime and FQC, and I've shown that a side is equal and one angle is equal. Now I need to show the other angle is equal. One sec, guys, I'll be right back. All right. So yeah, there was that observation I made way back that angle PFA is equal to angle QFN, but I couldn't prove it. So I have that if I could prove that, then I could solve the problem. Angle PFA equals angle QFN. Let's see. Well, maybe triangle PFM prime is congruent to triangle FQN. And maybe I could prove that differently. I feel like I'm so close, I just don't want to give up on this problem, but maybe I should if it's too long. Or maybe
Michael, is it true that B, A, C, and Q are cyclic?
BACQ.
Yes.
I would be surprised. No, because BAC is the circle that we've already drawn, right? So,
No. BACQ.
Oh, P?
Yes. No.
No.
It looks like.
That's all right. Yeah, I don't know if we could show PA prime is equal to QC. Maybe that would solve it. see.
I wonder if PQ passes through design KPQ passes through the center of this other circle. A prime P. It's the center.
Hold on just a second. Hey, Enrique. Thanks for joining us. Yeah. All right. So, what was your suggestion, Rodrigo?
Take the center of this circle, A prime, M prime, P. These five points, circle of these 5 points.
Okay.
And I guess it is on the line PQ.
Yes.
Yeah, looks
That's
like.
cool. Interesting. That is pretty cool. So, yeah, basically I proved that angle PA prime M is equal to angle QCF. And then I also know that FA prime is equal to FC. So if I could just show this third angle is equal, that would solve the problem. That's kind of what I'm thinking. But yeah, I've spent a while trying to do that. But maybe it would be better to show that this angle is equal. Angle FQC is equal to angle FPA prime. Let's see. We also know that FM is equal to FN. We know that yeah, I added a lot to it, so I'm not sure if this is really the best way to go around it. But yeah, or go about it. All right, I'll spend 5 more minutes on this, and then if we can't get it, I'll move on to the next problem. Let's see. Yeah, can we do an angle chase to show that angle PFA is equal to QFN? Yeah, that is interesting what you mentioned, how the center of it is collinear. Yeah, if we can show, well, if we can show M prime N is parallel to PQ, yeah, basically,
Yeah, showing M prime N is parallel to PQ, I think would solve the problem. And we know that F is the circumcenter of M prime Mn. So basically angle M prime NM is half of angle MFM prime. Now I'm kind of more optimistic. Wait, let me think about that one more time. So M prime NM is half of M prime FM, which is let's see. Wait, how did I even define M prime to begin with? Yeah, that's M prime FM is AFM. AFM is NFC. So is NFC equal to, let me try this. This is kind of interesting. NFC is 23, PKG. Yeah, but let's see. Interesting. So NFC and AFM, I think, are equal to this angle right here. Yes. I think I might have a really long proof here. Hold on just a sec. So yeah, I'm just thinking through this. Yeah, I kind of lost my train of thought, but yeah, if we can show M prime N is parallel to PQ, that proves that FPQ is isosceles, because that means basically since FM prime N is isosceles by definition, because M prime was a reflection of M over like the angle bisector of AFM. So yeah, if M prime N is parallel to PQ, that solves the problem. And I was thinking we could calculate so M prime
NM is half of M prime FM is half of PFM. Yes, just a second. Or no, that's half of, we want to show angle, we want to show angle AFM is equal to angle, this angle right here. So,
Hey, Michael.
yeah.
I think I've seen another approach that is something that we didn't try before. So can I think that's that will lead to good things. Can I say?
Yeah. Hold on one second. Let me finish this idea. I think I might
Yeah,
have just.
basically.
or,
Of course.
yeah, I'm sorry. I'm just. That's really interesting. That center H you mentioned is actually on the circumcircle of KA.
Oh my gosh.
Yeah. So, but all right. So I'm gonna. I think I have an idea for a solution, but I'm going to delete
Oh,
stuff
okay.
and try your solution. I'm gonna try your solution.
No. I didn't solve it. I was just proposing another thing.
Oh, you just kind of had an
Yeah.
idea? All right.
Yeah. It's very simple. You don't have to delete anything. Basically,
Okay.
if you take the midpoint of AC and the midpoint of PQ, you want to prove that these midpoints are concyclic with F and K. Yeah, and these midpoints lie in this midpoint. One of these midpoints, the midpoint of PQ, lies on that circle that passes through a total of 6 points.
Okay. So
You want to show FL, JK are cyclic, right?
yes. Interesting. FL. And yeah, which is the same as showing FL is perpendicular to KQ. There's so much structure here. Look at it. This is crazy.
So many things going on.
Yeah, because FO and J are collinear, right? So FJ is perpendicular to KC. And you said L is the midpoint of PQ, right?
Yes, it is.
Oh, L is not, yeah, that's not necessarily the diameter of that circle. It looked like it, but if you move the points around, so yeah, okay. So but I feel like that's kind of obvious because like if L is the midpoint of PQ, like yeah, I see what you did. Then basically if we can show FL is perpendicular, that would solve the problem. So yeah, like I see your approach. Let's see. All right. I am just going to go back to what I was thinking, just because I don't see immediately a solution there. But it's an interesting idea. Let's see. I wanted to show. Hold on one sec. Yeah, is it true? Yeah, AFMK is cyclic. Which is the same as saying that angle FAC is equal to A prime MI. So FCA let's see. Yeah, I want to show FMAK is cyclic. And that's actually obvious. Okay, so all right, so yeah, let me delete a couple things and then I can kind of start the proof from scratch. All right. Let me just make sure I have it all in my head for a sec. That. Just half of that. All right, I think I got it. Let me delete stuff and then start the proof from scratch. I've added so many points here. I'm just going to leave M prime and A prime there. Whoops. Yeah, we don't need all of these. In fact, I don't even know if I need A prime. Let's see. Let's see, what points did I add and what was already there? I'm just going to start out the proof like this. Okay, so, but yeah, I'm probably going to, the text is going to cover up the diagram, but oh well. So, okay, so F is the midpoint of arc. Right, I'll start out by defining M prime and A prime. So right. That's the first step. So then Fm is Fm prime and Fa is Fa prime. And then F is the midpoint of arc ABC, so FA equals FC. And then we can show FBMN is cyclic by an angle chase. So so yeah, I mean, in the problem we're given AM is equal to CN. I'll just say triangle FAM is congruent to triangle FNC, and look, and to see that you can view the video on Archimedes' theorem. So it's not that hard of a proof. So I have a video on that. Okay. And then, so M prime M, A prime A is cyclic. And then we also want to show that P lies on that circle. How did I get that? I'm trying to remember what I did. Or if I even need that for the proof. But basically, like, we have Fm is Fm prime is Fn. So F is the circumcenter of M prime N. And so basically, I want to show M prime N is parallel to PQ. So M prime NM is half of M prime FM. Which is half of angle AFM. Yeah, I don't even think I need this circle right here. And then we could show KA MF is cyclic. So basically by a spiral similarity, FMN is similar to FAC. I'm just going to write that out shortly here. Okay. And so that means that FMAK is cyclic because so FMAK is cyclic. And once we know that, So I was trying to do an angle chase. So M prime NM is half of AFM. So, and then AFM would be equal to a KM. So that means which is angle NKP, which is half of angle NKP. So if angle M prime NM is equal to angle NKP, that means that M prime N is parallel to PQ. I don't even know if we needed A prime. I don't think we did. Yeah, A prime is irrelevant. So yeah, I could just and so since Fm prime n is isosceles, that means FPQ is isosceles. Yeah, so all right. And so that means that FP equals FQ. That was a fun one. I really didn't think we'd get through it. Let me see. Did everything I did make sense? Let's see. A is equal to FC. So M n prime n is half yeah, I think that's right.